Picture the universe not as a static, unchanging void, but as a vast, dynamic stage where galaxies, massive islands of stars, gas, and dust, are in constant motion, drawn together by an invisible force. Now, envision two of these galactic giants, each holding hundreds of billions of stars, racing toward one another at speeds so immense they defy comprehension. This isn't science fiction, it's the breathtaking reality of galactic collisions, some of the most violent and transformative events in the cosmos. Yet within this chaos lies a paradox. These cataclysmic encounters are also the universe's way of creating something new. Gravity, the silent architect of the cosmos, weaves these galaxies together, twisting their shapes, igniting bursts of star formation, and even merging supermassive black holes at their hearts. The result: a celestial masterpiece, a reborn galaxy unlike anything that existed before. What makes these collisions so extraordinary isn't just their scale or their destructive power, it's their creative force. Every time galaxies collide, they rewrite their own futures. Stars are flung into new orbits, gas clouds collapse under gravity's relentless pull, and entire solar systems are reshuffled. And here's the most astonishing part. This isn't some rare, distant phenomenon. Our own Milky Way is on a collision course with the Andromeda galaxy, a slow-motion dance that will unfold over billions of years. That means the night sky our distant descendants see will be utterly transformed, filled with new constellations and brilliant lighting up the darkness. Galactic collisions aren't just something that happens out there, they're part of our cosmic destiny. So how does gravity choreograph this grand celestial ballet? How do galaxies, seemingly so vast and sturdy, bend and warp under its influence? And what can these collisions teach us about the universe's past and its future? In this journey, we'll unravel the secrets of these cosmic encounters, from the way gravity tugs at stars like an invisible puppeteer to the way black holes, hidden in galactic cores, eventually spiral together in a final, titanic embrace. By the end, you'll see the universe not as a static backdrop, but as a living, evolving tapestry, where even the most violent events are part of a grander story of creation. Ready to dive in? Let's explore the dramatic interplay of gravity and the stunning beauty of galactic collisions. To truly grasp the staggering scale of galactic collisions, let's zoom out beyond our familiar night sky. Imagine two galaxies, each a swirling metropolis of stars, separated by millions of light years. Despite the vast emptiness between them, gravity's pull is relentless, drawing them together over eons. This isn't a sudden crash, it's a slow, inevitable dance, unfolding over timescales so immense they make Earth's entire history feel like a blink. Take the Milky Way and Andromeda, for example. Right now, they're hurtling toward each other at around 110 kilometers per second. But even at that speed, their collision won't happen for another 4 billion years. That's how mind-bendingly large these structures are. And when they finally meet, the encounter will be less like a head-on crash and more like two swirling storms merging, their stars weaving through one another in an intricate gravitational ballet. What's astonishing is how gravity reshapes these galaxies long before they even touch. As they draw closer, tidal forces, the same pull that creates ocean tides on Earth, start stretching their spiral arms into long, luminous streamers. Gas clouds, once calm and dispersed, slam together, compressing under gravity's grip until they ignite into dazzling bursts of new stars. These starburst regions can outshine entire galaxies, painting the collision in brilliant blues and whites as young, massive stars flare to life. Yet amid this chaos, something remarkable happens. Most stars don't actually collide. Galaxies are mostly empty space, with stars so far apart that direct impacts are rare. Instead, gravity reshuffles them like a cosmic deck of cards, flinging some into wild new orbits while others are ejected entirely, becoming lone wanderers in the intergalactic void. Over billions of years, the two galaxies lose their original shapes, merging into something entirely new, a larger elliptical galaxy, its stars now bound by a shared gravity. This process isn't unique to our corner of the universe. Look deep into the cosmos, and you'll find countless galaxies caught in mid-collision, their distorted forms frozen in time by the vast distances their light traveled to reach us. Some, like the antennae galaxies, are already entangled, their long tidal tails stretching across space like celestial brushstrokes. Others, like the mice galaxies, are in the early stages, their shapes just beginning to warp under each other's pull. Each collision is a snapshot of gravity's patient, creative destruction, a reminder that even the mightiest structures in the universe are never truly still. So why does this matter to us? Because galactic collisions aren't just spectacle, they're engines of change. They recycle gas, forge new stars, and even seed the universe with heavier elements essential for planets and life. Without these cosmic encounters, the universe as we know it wouldn't exist. And in the distant future, when the Milky Way and Andromeda finally merge, their combined gravity might just set the stage for new worlds, and perhaps new possibilities we can't yet imagine. Gravity doesn't just bring galaxies together, it sculpts the very fabric of the universe itself. Think of space-time as an infinite, stretchable sheet, and every massive object, a star, a planet, or an entire galaxy, as a weight pressing down on it. The heavier the object, the deeper the dent it creates, warping the paths of everything moving nearby. This is revolutionary insight. Gravity isn't some mysterious force acting across empty space. It's the bending of space-time itself, a cosmic curvature that guides the motion of celestial bodies like grooves on a winding road. When two galaxies approach each other, their immense gravity wells begin to interact, twisting space-time like a pair of dancers pulling at each other's fabric. Stars and gas clouds no longer move in straight lines but follow these warped contours, spiraling toward one another in a slow, inevitable embrace. Even light bends around these distortions, a phenomenon called gravitational lensing, allowing us to see distant galaxies stretched into shimmering arcs, as if the universe itself were a funhouse mirror. But gravity's role doesn't end with collisions. It's the architect of cosmic structure on every scale. Without it, the universe would be a formless sea of scattered matter, never clumping into galaxies, stars, or planets. After the Big Bang, tiny fluctuations in density gave gravity its first foothold, letting it amplify these imperfections over billions of years. Like a sculptor shaping clay, gravity gathered gas into stars, stars into galaxies, and galaxies into vast clusters connected by filamentary webs of dark matter. Structures so enormous they stretch across hundreds of millions of light years. And here's the twist: gravity's work is never done. Even as it builds, it also destroys. Supermassive black holes lurking at the hearts of galaxies grow by devouring surrounding material, their gravity so fierce it can rip stars apart. Yet these same black holes, when they collide, release energy so intense it sends ripples through space-time itself, gravitational waves that scientists can now detect here on Earth. These waves are like cosmic fingerprints, revealing the universe's most violent events in ways light alone never could. So what does this mean for the future? Gravity's grip ensures that galaxies will continue merging, reshaping, and evolving. But over trillions of years, as the universe expands faster and faster, gravity may face its ultimate limit. Distant galaxies will fade from view, their light stretched beyond detection, and the cosmos will grow cold and dark. Yet even then, gravity will still hold sway, binding what remains in an endless, silent dance, proof that the universe's greatest architect never truly rests. Galactic collisions come in many forms, each leaving its own spectacular mark on the universe. The most dramatic are major mergers, where two galaxies of similar size spiral together in a slow, gravitational embrace. Picture two titans like the Milky Way and Andromeda, each with hundreds of billions of stars, drawn into a dance that will last billions of years. When galaxies of equal mass collide, their mutual gravity pulls them into increasingly orbits until their stars, gas, and dark matter become irreversibly entangled. The result? A completely new galaxy, often oval-shaped, its original spiral arms now stretched and scrambled into a glowing, chaotic haze. But not all mergers are created equal. In minor collisions, a larger galaxy, like our Milky Way, swallows a much smaller neighbor, absorbing its stars without losing its fundamental structure. The smaller galaxy doesn't vanish without a trace, though. Look at the Sagittarius Dwarf galaxy, currently being torn apart by the Milky Way's gravity, its stars strewn across our sky in shimmering streams. These stellar trails, called tidal debris, are like cosmic breadcrumbs, marking the smaller galaxy's final journey. Then there are the near misses, galaxies that don't collide head-on but pass close enough for gravity to wreak havoc. Like a celestial brushstroke, these encounters stretch galaxies into surreal shapes, with long ribbons of stars and gas flung into space. The Whirlpool Galaxy, for instance, sports majestic spiral arms amplified by a recent gravitational tug-of-war with a smaller companion. And the Tadpole Galaxy. Its spectacular 300,000 light-year-long tail is the aftermath of a close shave, a trail of stars ripped loose by a passing neighbor. What makes each collision unique is just the outcome, but the way it transforms the galaxies involved. Major mergers ignite frenzied starbursts as gas clouds crash together, while minor ones quietly repaint the night sky with stolen stars. Even near misses, though fleeting, leave galaxies permanently altered, their shapes twisted, their futures rewritten. And in every case, gravity is the artist, sculpting the cosmos one collision at a time. These events aren't just beautiful, they're vital. Without galactic collisions, the universe would lack the rich diversity of galaxies we see today. They recycle gas, spark new generations of stars, and even seed the cosmos with the heavy elements needed for planets and life. So the next time you gaze at the night sky, remember, the serene glow of galaxies hides a dynamic, ever-changing universe, where even the most violent encounters are threads in a grand cosmic tapestry. Dark matter is the unseen hand guiding every galactic collision, an invisible force that shapes the fate of galaxies without ever revealing itself. Though we can't see it directly, its presence is undeniable, like a puppeteer pulling strings behind a cosmic curtain. In fact, dark matter makes up about 85% of a galaxy's total mass, meaning the stars and gas we observe are just the glittering tip of an enormous, hidden iceberg. When galaxies collide, it's their vast halos of dark matter that meet first, their gravitational pull sculpting the entire encounter long before their visible stars begin to intertwine. Picture two galaxies approaching each other in the void of space. Their luminous spiral arms may be millions of light-years apart, but their dark matter halos, extending far beyond the visible edges, are already locked in a silent tug-of-war. These halos act like gravitational blueprints, bending the paths of stars and gas clouds as they pass through. Computer simulations reveal something astonishing. Without dark matter's influence, galaxies would simply glide past one another like ships in the night. It's the sheer mass of these invisible halos that slows them down, ensuring they eventually merge into a single, larger galaxy. But dark matter doesn't just orchestrate the collision, it also determines its aftermath. In some mergers, dark matter's distribution can fling stars into chaotic new orbits, stretching galaxies into bizarre shapes. In others, it acts like an anchor, stabilizing the newly formed galaxy and preventing it from tearing itself apart. The antennae galaxies, for example, showcase this delicate balance. Their long, luminous tails of stars were carved out by dark matter's gravitational tides, yet their cores remain intact, held together by its unseen grip. The mystery deepens when we consider how dark matter behaves during these encounters. Unlike stars, which rarely collide, or gas clouds, which crash together and ignite new stars, dark matter particles pass right through one another, interacting only through gravity. This means dark matter halos can merge smoothly, while the visible galaxies they host are twisted and reshaped. It's as if two crowds of people walk through each other effortlessly, while their shadows tangled in an elaborate dance. Understanding dark matter isn't just about solving a cosmic puzzle, it's about decoding the very framework of the universe. Without it, galaxies wouldn't have formed in the first place, and collisions would lack the gravitational glue needed to create something new. Every time we observe a galactic merger, we're glimpsing the hidden architecture of the cosmos, where dark matter's silent influence writes the rules of engagement. And now, as these titanic collisions unfold, another spectacle begins, one where chaos gives birth to creation. When galaxies merge, their gas clouds don't just drift apart, they collide, compress, and ignite in brilliant bursts of star formation. But that's a story for the next chapter in this cosmic saga. When galaxies collide, they don't just rearrange stars, they set off cosmic fireworks. As two galaxies spiral together, their immense gravity squeezes vast clouds of gas and dust, compressing them until they reach a breaking point. Suddenly, these clouds collapse under their own weight, igniting thousands, sometimes millions, of new stars in a dazzling explosion of light. This is the birth of a starburst galaxy, where star formation rates skyrocket to hundreds or even thousands of times what we see in ordinary galaxies like our Milky Way. The antennae galaxies offer one of the most spectacular examples. Once two separate spiral galaxies, their collision has birthed a frenzy of blue-white star clusters, each one a nursery of young, massive stars burning fiercely against the darkness. These stars are the universe's short-lived, brilliant, and intense. Their blue glow dominates the galaxy's tangled cores, outshining everything around them. But this brilliance comes at a cost. Starbursts devour gas at an astonishing rate, exhausting the very fuel needed to make more stars in just a few million years, a blink on cosmic timescales. What's fascinating is how these starbursts sculpt galaxies long after the fireworks fade. The most massive stars burn out quickly, exploding as supernovae and scattering heavy elements like carbon, oxygen, and iron into space. These elements become the building blocks for future stars, planets, and even life. Meanwhile, the surviving stars, those not flung into intergalactic space, settle into new orbits, giving the merged galaxy its final shape. A starburst isn't just a spectacle, it's a galaxy's way of reinventing itself. Yet amid this stellar chaos, another drama unfolds, one hidden from view. At the very heart of these colliding galaxies, supermassive black holes, each millions or even billions of times heavier than our Sun, begin their own gravitational dance. Drawn together by the same forces reshaping their host galaxies, these cosmic titans spiral closer, destined for a collision of their own. And when they finally meet, the energy released will shake the very fabric of space-time. At the heart of every galaxy lies a monster, a supermassive black hole, an object so dense that not even light can escape its grip. When galaxies collide, these cosmic titans awaken from their slumber, drawn together by the same gravitational forces reshaping their stellar homes. Picture two black holes, each millions or even billions of times heavier than our Sun, locked in a slow, spiraling dance. As they circle closer, their immense gravity warps space-time itself, sending ripples across the cosmos like waves from a stone dropped in a pond. These are gravitational waves, distortions in the fabric of reality predicted by over a century ago and now detectable by observatories here on Earth. The final moments of this dance are nothing short of apocalyptic. As the black holes merge, they release energy equivalent to billions of supernovae exploding simultaneously, a burst so powerful it briefly outshines every star in the observable universe combined. This isn't just theoretical. In 2015, the LIGO Observatory made history by detecting gravitational waves from merging stellar mass black holes, but supermassive mergers. Their signals are 1,000 times stronger, humming at frequencies so low they'll require space-based detectors like LISA, set to launch in the 2030s to hear their cosmic chorus. What makes these mergers so fascinating isn't just their scale, it's what they reveal about the universe. When black holes collide, they put theory of general relativity to the ultimate test. Do their gravitational waves behave exactly as predicted, or might they hint at new physics? Some scientists even speculate that merging black holes could warp spacetime so severely they create fleeting, wormholes hypothetical tunnels through the cosmos. While that remains speculative, one thing is certain. These collisions are cosmic laboratories, offering glimpses into gravity's most extreme regime. Yet the aftermath of a black hole merger is just as transformative. The newly formed supermassive black hole, now even more massive, recoils from the collision with a kick so violent it can rocket through its host galaxy at speeds exceeding 5,000 kilometers per second. Imagine a bullet the size of a solar system, propelled by pure gravitational force. This recoil can eject stars from their orbits, strip gas from the galactic core, and even send the black hole itself flying into intergalactic space, though most remain anchored by the galaxy's collective gravity. But the story doesn't end there. As the merged black hole settles, it feasts on the gas and stars stirred up by the collision, growing even larger and powering brilliant quasars, beacons of light visible across the universe. These quasars, fueled by infalling matter, can outshine their host galaxies, their radiation sculpting the surrounding cosmos like a cosmic lighthouse. In this way, black hole mergers don't just destroy, they create, seeding the universe with the energy and turbulence needed to birth new stars and shape galaxies for eons to come. And now, as the dust settles from these titanic encounters, another process begins, one where chaos gives way to order and scattered cosmic material finds new purpose. The collision's shockwaves compress gas clouds, triggering fresh waves of star formation, while streams of ejected stars paint the galactic outskirts with stolen light. This recycling of matter from destruction to creation is the universe's way of turning chaos into something new, a cycle as old as time itself. When galaxies collide, they don't just merge. They splatter cosmic debris across the universe in breathtaking displays of gravitational artistry. These luminous trails of stars and gas, known as tidal tails, are gravity's signature, stretching like celestial brushstrokes across thousands of light years. Take the mice galaxies, their long, entwined tails resembling the whiskers of their namesake, each starry filament a testament to the immense forces at work. But these aren't just pretty cosmic accidents. They're forensic evidence, telling the story of how galaxies interact, distort, and ultimately transform one another. What's astonishing is how these structures form. As two galaxies draw near, their mutual gravity creates tidal forces, the same phenomenon that pulls Earth's oceans into high and low tides, but on a galactic scale. The side of a galaxy closest to its neighbor feels a stronger pull than the far side, stretching it like taffy. Stars and gas clouds caught in this gravitational tug-of-war are flung outward, forming those dramatic arcs we observe. Some material escapes entirely, becoming intergalactic orphans drifting through the void. Other streams, still bound by gravity's grasp, curve back toward the galaxies in elegant loops, as if the universe itself is reluctant to let go. The fate of this debris is just as fascinating as its creation. Over millions of years, some of these exiled stars may fall back into the merged galaxy, enriching it with fresh material for future generations of stars. The rest become cosmic nomads, wandering the space between galaxies in vast, diffuse clouds. These wandering stars aren't lost, though. They're potential seeds for new structures, or even the building blocks of future dwarf galaxies. In fact, astronomers have spotted entire star streams in our own Milky Way, remnants of smaller galaxies torn apart by our galaxy's gravity. their stars now tracing ghostly rivers across our night sky. Studying tidal tails is like reading a galactic history book. Their shapes, lengths, and compositions reveal the angle, speed, and timing of past collisions. For instance, long, thin tails suggest a fast, glancing encounter, while shorter, twisted ones hint at a slower, more drawn-out merger. By mapping these structures, scientists can reconstruct events that happened billions of years ago, piecing together how galaxies grew and evolved over cosmic time. But the story doesn't end there. These collisions don't just leave behind stellar wreckage, they fundamentally reshape the galaxies involved. As tidal tails carry away gas and stars, they also strip galaxies of the raw materials needed for future star formation, altering their destinies. Yet paradoxically, the same collisions compress remaining gas clouds, sparking bursts of new. It's this push and pull between destruction and creation, loss and renewal, that makes galactic collisions such powerful engines of cosmic change. And as we look deeper into the universe, we find these tidal tails everywhere, each one a snapshot of gravity's relentless work. From the antennae galaxy's shimmering arcs to the tadpole galaxy's spectacular tail, these structures remind us that even the mightiest galaxies are not islands unto themselves, but part of a vast, interconnected tapestry, one where every collision leaves an indelible mark on the universe's ever-evolving story. Galaxies aren't born as the majestic spirals and smooth ellipticals we see today. They're forged through fire, shaped by countless collisions over billions of years. Think of a spiral galaxy like our Milky Way as a delicate, spinning top. Its elegant arms, rich with gas and young stars, depend on a fragile balance. But when another galaxy crashes into it, that balance shatters. Gravity's relentless pull twists those spiral arms beyond recognition, scattering stars into chaotic orbits and draining away the gas that fuels new star formation. What remains is often an elliptical galaxy, a featureless, football-shaped swarm of older stars, its once vibrant structure erased by the violence of the merger. This transformation isn't just destruction, it's a cosmic metamorphosis. Early in the universe's history, galaxies were smaller, gas-rich, and primed for collision. When these young galaxies merged, their abundant gas reservoirs collided head-on, igniting frenzied starbursts that built up their stellar populations rapidly. Over time, these mergers created the massive galaxies we observe today, their growth fueled by an era of cosmic bumper cars. Without these ancient collisions, galaxies might have remained petite and isolated, leaving the universe sparse and dim. But why do mergers tend to erase spiral structures? The answer lies in gravity's chaotic influence. Spiral arms rely on orderly rotation, with stars moving in synchronized orbits. During a collision, gravitational forces jumble these orbits, randomizing stellar motions until the galaxy's rotation is overwhelmed. Gas, the lifeblood of spiral arms, gets either funneled toward the galactic center to feed a growing black hole or blown entirely out of the galaxy by shockwaves from newborn stars. The result is a galaxy that's all bulge and no disk, its stars aging without replenishment, its spiral arms a distant memory. Yet even in this apparent simplicity, elliptical galaxies hold clues to their violent pasts. Some exhibit faint shells or ripples, ghostly echoes of past mergers, like concentric waves frozen in time. Others rotate in unexpected ways, their stars moving in disordered paths that betray their turbulent origins. These cosmic fingerprints allow astronomers to reconstruct a galaxy's history, revealing how many mergers it survived and what kinds of galaxies it consumed along the way. The story doesn't end with ellipticals, though. Collisions also birth hybrid galaxies, peculiar blends of spiral and elliptical features. Take Messier 87, the supergiant elliptical galaxy at the heart of the Virgo cluster. Its smooth outer halo hides a dynamic core, where a jet of particles erupts from a supermassive black hole. This mix of serene outskirts and violent center hints at a complex merger history, one that didn't just erase structure but repurposed it. Looking deeper into the universe means looking further back in time, and there we find galaxies in the throes of their most transformative collisions. The early universe was a construction zone, with galaxies merging so frequently that some grew to enormous sizes in just a few billion years. These ancient mergers didn't just build galaxies, they set the stage for everything that followed, seeding the cosmos with the raw materials for stars, planets, and life itself. Without these primordial encounters, the night sky as we know it wouldn't exist. And now, as we peer back toward the dawn of galaxies, we uncover an even more dramatic truth. The first collisions didn't just shape individual galaxies, they laid the foundation for the universe's large-scale structure, weaving the cosmic web that connects all matter across the vastness of space. To witness the dawn of galactic collisions, we must journey back over 13 billion years, a time when the universe was young, dense, and teeming with chaos. Back then, galaxies weren't the majestic spirals or stately ellipticals we see today. They were smaller, and packed so tightly that collisions happened 10 times more often than they do now. Imagine a cosmic freeway during rush hour where galaxies, some no larger than today's star clusters, zipped past one another, frequently grazing or merging in spectacular bursts of creation. The Space Telescope has given us front-row seats to these ancient encounters. Peering into the ultra-deep field, it captured faint, distorted shapes, galaxies stretched like taffy, their forms warped by violent gravitational encounters. These weren't the clean, defined spirals of the modern universe, but messy, blobby structures, bloated with gas and glowing with the blue fire of newborn stars. In one remarkable image, two adolescent galaxies, dubbed the tadpole galaxies of the early universe, are caught mid-collision, their long tails of stars and gas unfurling like cosmic ribbons. What made these early mergers so different? For one, galaxies back then were gas-rich, up to 10 times more than today's galaxies. When they collided, this abundant fuel ignited frenzied starbursts, lighting up the early cosmos like fireworks. These weren't the measured, billion-year dances we see now. They were rapid, violent affairs, with galaxies merging in just a few 100 million years. And because the universe was smaller, these collisions didn't just shape individual galaxies. They built the first galactic scaffolding, weaving the threads of what would become the cosmic web. But how do we study events so impossibly distant? Light from these ancient collisions has traveled for billions of years to reach us, stretched and reddened by the expansion of the universe. Telescopes like in JWST act as time machines, capturing this light and translating it into images we can analyze. By examining the chemistry of these primordial galaxies, their ratios of hydrogen, helium, and trace metals, we can reconstruct their collision histories. For instance, a sudden spike in heavy elements often signals a past merger, where compressed gas clouds triggered waves of star formation, forging new elements in stellar furnaces. These observations reveal something profound. Today's giant galaxies didn't form in isolation. They're the products of countless mergers, each one adding stars, gas, and dark matter to their growing bulk. The Milky Way, for all its current solitude, likely began as a handful of tiny proto-galaxies that collided and merged in the universe's first few billion years. Even now, it continues to cannibalize smaller neighbors, like the ongoing digestion of the Sagittarius Dwarf galaxy. The early universe's collision frenzy wasn't just a phase, it was the foundation of everything we see today. Without those ancient mergers, galaxies might have remained small and sparse, leaving the cosmos dark and unpopulated. But gravity had other plans, weaving chaos into structure, destruction into creation, and painting the universe with the brilliant aftermath of countless cosmic crashes. Now armed with ever more powerful telescopes, we're not just looking back in time, we're uncovering the very recipes of galactic growth. From the violent origins of the first supermassive black holes to the way dark matter guided these early mergers, each discovery peels back another layer of the universe's turbulent youth. And as we piece together this cosmic puzzle, one collision at a time, we're rewriting the story of how galaxies, and by extension, we ourselves, came to be. The next chapter in this saga unfolds with modern observatories, where cutting-edge technology lets us watch mergers unfold in real time, revealing details our ancestors could only dream of glimpsing. From radio waves to gravitational ripples, we're no longer passive observers but active witnesses to gravity's endless dance. For centuries, galaxies appeared as static smudges of light in our telescopes, frozen portraits of a seemingly unchanging cosmos. Then came, with its crystal-clear vision piercing 13 billion years into the past, revealing a universe alive with motion. Its iconic deep-field images didn't just capture distant galaxies, they froze them mid-collision, their distorted shapes telling stories of gravitational tug-of-war unfolding over eons. One remarkable snapshot shows the antennae galaxies, two spirals locked in a slow-motion crash, their long tails of stars flung into space like glitter from a shattered snow globe. Ultraviolet eyes caught the blue blaze of newborn stars igniting where their gas clouds collided, proof that destruction and creation are two sides of the same cosmic coin. But had limitations. Dust, the same veil that obscures the heart of our own Milky Way, blocked its view of galactic cores where mergers unleash their most violent fireworks. Enter JWST, the infrared maestro. Where saw darkness, JWST's heat-sensitive vision unveils stars forming in the densest dust clouds, black holes feasting on superheated gas, and even the faint glow of ancient galaxies merging in the universe's infancy. Take the Pandora cluster. Saw a hazy gathering of galaxies, but JWST revealed a sprawling collision of at least 4 galaxy clusters. A gravitational pileup warping space-time itself into a funhouse mirror that magnifies even more distant mergers behind it. Meanwhile, down on Earth, radio telescopes like ALMA trace the invisible. While optical telescopes show the stars, ALMA maps the cold gas between them, the raw material for future collisions. By measuring the shifts of this gas, astronomers can reconstruct galactic motions in 3 dimensions, watching as gravity bends their paths toward inevitable mergers. And when it comes to tracking supermassive black holes spiraling toward collision, nothing beats the Event Horizon Telescope's planet-sized array, which captured the first-ever black hole shadow and now hunts for pairs on collision courses. This multi-wavelength approach isn't just about pretty pictures. By combining visible light snapshots, JWST's infrared revelations, and ALMA's molecular maps, scientists can simulate galactic collisions with startling accuracy. Supercomputers crunch this data into models that predict how the Milky Way and Andromeda will dance in 4 billion years, their first close pass, the way their spiral arms will shred into tidal tails, even the final merger that will leave a single elliptical galaxy in their place. These aren't just hypotheticals. We've observed galaxies at every stage of this process, creating a cosmic of our own future. Yet the most profound revelation isn't about any single collision. It's how telescopes have exposed the universality of the process. From the young cosmos, where tiny proto-galaxies clump together like wet sand, to the modern era of grand spirals and ellipticals, mergers are the universe's way of building. Every galaxy we see, including our own, carries the scars and souvenirs of past collisions, streams of orphaned stars, oddly angled spins, even the supermassive black holes at their cores. The night sky isn't a gallery of isolated masterpieces. It's a living collage, still being painted by gravity's patient hand. And now, as we turn our gaze from the distant universe to our own galactic neighborhood, a question emerges. If collisions shaped galaxies across cosmic time, what does that mean for the Milky Way? Our home galaxy isn't just a spectator to this drama, it's a participant, with a collision timeline written in the stars above us. The evidence is all around if you know where to look. Right now, the Andromeda galaxy is hurtling toward us at roughly 110 kilometers per second, so fast it could cross the United States in under a minute. But don't panic just yet. At that speed, it'll still take around 4.5 billion years before it actually reaches us. When it does, the collision won't be the fiery explosion you might imagine. Galaxies are mostly empty space, so the stars within them, including our Sun, will likely slip past one another like two swarms of bees merging in midair. But gravity's invisible hand will reshape everything. Over the course of billions of years, the Milky Way and Andromeda will swing past each other in a series of ever-tightening loops, their spiral arms stretched into luminous tidal streams. Each pass will strip away more of their original structure, flinging stars into wild new orbits while their central black holes spiral closer. By the time the dance ends, the two galaxies will have merged into a single elliptical galaxy. Astronomers call it a golden-hued giant devoid of the delicate spiral arms we know today. What does this mean for Earth? Remarkably, our solar system will probably survive, though it might get a new cosmic address. Simulations suggest we could be flung much farther from the galactic core, or even tossed into the outskirts entirely. But the real spectacle will be overhead. As the galaxies merge, the night sky will transform. Andromeda, which today appears as a faint smudge in the constellation bearing its name, will grow larger and brighter with each passing epoch. Eventually, it'll dominate the heavens, its stars mingling with ours in a dazzling, unfamiliar tapestry. New constellations will emerge, stitched together from stars born in both galaxies. This collision isn't just a distant spectacle, it's a mirror reflecting our past. The Milky Way didn't start as the grand spiral we see today. It grew by devouring smaller galaxies, and their stars still drift through our halo like ghosts. The coming merger with Andromeda is just the next chapter in a story that's been unfolding for billions of years. Far from being catastrophic, it's a natural part of galactic evolution, a process that's shaped the universe since its earliest days. And while 4.5 billion years sounds impossibly remote, it's a reminder that the cosmos is never truly still. Galaxies collide, stars are born and die, and the universe reinvents itself on scales we can barely fathom. The Milky Way and Andromeda's fate isn't unique. It's a preview of what's happening in countless other corners of the cosmos, where gravity weaves galaxies together in an endless dance of destruction and renewal. Up next, we'll zoom out even further to see how these collisions don't just reshape individual galaxies. They build the largest structures in the universe, from vast clusters to the cosmic web itself. Because when galaxies collide, the ripple effects stretch far beyond what meets the eye. The universe isn't just a scattering of isolated galaxies. It's a vast, interconnected tapestry, woven together by invisible threads of dark matter. Picture this: colossal filaments of this mysterious substance stretch across billions of light years, forming a cosmic web where galaxies cluster like dewdrops on a spider's silk. These filaments aren't just passive scaffolding, they're cosmic highways guiding galaxies toward one another in a slow-motion ballet dictated by gravity. When galaxies collide along these dark matter strands, they don't just merge, they feed the largest structures in the universe. Superclusters, sprawling metropolises of galaxies bound together in a gravitational embrace. Take the supercluster, our home in the cosmos. This enormous structure, spanning 500 million light-years, contains over 100,000 galaxies, including the Milky Way. Like rivers flowing into a delta, galaxies move along dark matter filaments toward its center, a region astronomers call the Great Attractor. These collisions and migrations aren't random. They're part of a grand choreography, where gravity pulls galaxies into dense knots at the intersections of filaments, leaving vast voids between them. The result? A universe that looks less like a uniform scatter of stars and more like a frothy sea of galaxy clusters, connected by delicate bridges of dark matter. But how do these collisions shape the web itself? Every time galaxies merge, they send ripples through the cosmic structure. Dark matter halos, the invisible skeletons of galaxies, grow denser and more massive, amplifying their gravitational pull. Gas stripped from colliding galaxies flows along filaments, fueling new star formation in distant clusters. Even black holes play a role. Their mergers release energy that can heat surrounding gas, pushing it away and altering how matter accumulates. Over billions of years, these interactions don't just build galaxies. They sculpt the universe's very architecture, determining where new galaxies will form and how they'll move. This brings us to one of the cosmos' most dramatic phenomena, galactic cannibalism. In dense clusters like Coma or Virgo, giant elliptical galaxies lurk at the center, growing ever larger by devouring their neighbors. These cluster galaxies are the universe's apex predators, their immense gravity tearing apart smaller galaxies that stray too close. The evidence is etched in the stars, streams of stolen starlight, shells of displaced gas, and even the odd galactic corpse, its stars now assimilated into the predator's halo. Yet even this violence has purpose. As cannibal galaxies grow, they anchor their clusters, their gravity preventing smaller galaxies from drifting into the void. The recycled gas and stars from their meals become raw materials for future generations of stars. In this way, the cosmic web isn't just a backdrop for collisions. It's a dynamic, ever-evolving network where destruction and creation are forever intertwined. And as we map its filaments with telescopes like Euclid and the Dark Energy Survey, we're not just charting the universe's present, we're tracing the history of how gravity built everything we see. The story doesn't end there. Beyond the visible web lies an even deeper mystery, dark energy, the force accelerating the universe's expansion. As galaxies collide and clusters grow, they're also racing against this relentless tide, their gravitational bonds tested by the cosmos' expanding fabric. One day, distant galaxies will vanish beyond our horizon, their light stretched too far to see. But for now, the cosmic web remains a testament to gravity's enduring power, a reminder that even the mightiest structures in the universe are threads in a grander design, woven together by collisions we're only beginning to understand. Galactic cannibalism sounds like something from a cosmic horror story, but it's actually one of the universe's most common and delicate processes. Unlike the violent head-on collisions of two spiral galaxies, these mergers are more like a slow, methodical feast. Picture a massive galaxy, its gravity reaching out like invisible tendrils, gently pulling a smaller neighbor apart over billions of years. The Milky Way is no stranger to this behavior. Right now, it's in the process of digesting the Sagittarius Dwarf galaxy, whose stars are strewn across our sky in shimmering, ghostly arcs. These stellar streams, as they're called, are the remnants of countless smaller galaxies consumed by our own, their stars now orbiting in elongated ribbons that trace their tragic history. But why does this happen? Smaller galaxies, often rich in gas and stars but lacking the gravitational muscle to resist, are drawn into the orbit of larger ones. As they loop closer, tidal forces, the same gravitational tug that creates ocean tides, begin stripping away their outer layers. Stars are plucked from the dwarf galaxy's grasp, forming those luminous trails we observe. The process isn't quick. It can take billions of years for a galaxy to be fully absorbed. And while it might seem destructive, it's also a vital part of cosmic growth. Every time the Milky Way consumes a smaller companion, it gains fresh stars, gas, and even dark matter, subtly reshaping its structure and fueling future star formation. The evidence of this cannibalism is everywhere, if you know where to look. Beyond Sagittarius, there's the Stream, a group of stars orbiting the Milky Way's halo, believed to be the remains of another dwarf galaxy devoured long ago. Then there's Gaia Enceladus, a colossal relic of a merger that occurred 8 to 10 billion years ago, whose stars now make up a significant portion of our galaxy's outer reaches. These ancient collisions didn't just add stars. They may have triggered bursts of star formation, seeding the Milky Way with the building blocks of future solar systems. What's fascinating is how these mergers differ from major collisions. When two large galaxies collide, the chaos is immediate and dramatic. Spiral arms shredded, gas clouds ignited, black holes sent spiraling. But galactic cannibalism is a quieter affair. The smaller galaxy's stars are gradually scattered, its gas siphoned away, its dark matter halo absorbed. There's no dazzling starburst, no titanic black hole merger, just a slow, inexorable assimilation, yet the impact is profound. Over time, these minor mergers can double a galaxy's mass, turning a modest spiral into a behemoth like Andromeda, which bears the scars of countless past meals. This raises an intriguing question. What happens to star systems like ours when galaxies merge? Could our solar system be flung into intergalactic space or tossed into a new orbit around the galactic core? The answer lies in the delicate interplay of gravity and chaos, a dance that shapes not just galaxies, but the fate of every star within them. When galaxies collide, it might seem like a recipe for cosmic disaster. Planets torn from their orbits, stars smashing together in fiery explosions. But the reality is far less dramatic. Picture our solar system as a tiny speck drifting through the vast emptiness of the Milky Way. The nearest star to our sun is over 4 light-years away. That's about 40 trillion kilometers of near-nothingness. Now scale that up to an entire galaxy, where stars are scattered even more sparsely. When two galaxies merge, their stars slip past each other like ships in the night, with the odds of a direct collision vanishingly small. That doesn't mean solar systems emerge completely unscathed, though. Gravity, the unseen puppeteer, can still wreak havoc. As galaxies intertwine, their gravitational forces tug at stars and planets, altering orbits in subtle or occasionally drastic ways. Some planets might be flung into wider, more elliptical paths around their stars, while others could be ejected entirely, cast adrift as rogue worlds wandering the interstellar void. Imagine Earth ripped from the sun's warmth, becoming a frozen nomad in the darkness. It's a chilling thought, but thankfully an unlikely one for us. Over the Milky Way's long history, our solar system has likely weathered multiple galactic mergers without catastrophe, a testament to both luck and the forgiving emptiness of space. What's truly remarkable is how these events leave their mark on surviving solar systems. Stars born from the gas-rich chaos of mergers often host planetary systems with wild, tilted orbits, a lingering signature of their turbulent origins. Others, like ours, might have been nudged into quieter corners of the galaxy, spared the worst of the gravitational turmoil. Even the comets and asteroids in our outer solar system could carry traces of ancient collisions, their erratic paths shaped by long-ago encounters with passing stars during mergers. This resilience isn't just a quirk of our cosmic neighborhood, it's a universal truth. Across the galaxy, countless solar systems have endured the same gravitational storms, their planets orbiting steadfastly despite the chaos around them. It's a humbling reminder that even in a universe of colossal forces and violent encounters, stability can persist. And as we look deeper into the cosmos, we find that these collisions don't just leave behind survivors. They forge entirely new kinds of galaxies, each one a unique masterpiece sculpted by gravity's relentless hand. Among the rarest and most striking results of galactic collisions are ring galaxies, cosmic bullseyes where stars blaze in a near-perfect circle against the darkness. Picture a spiral galaxy, serene and orderly, suddenly pierced by a smaller intruder. Like a stone dropped into a pond, the impact sends shockwaves rippling outward, compressing gas and dust into a dazzling ring of newborn stars. The most famous example's object floats in space like a celestial jewel, its golden core encircled by a sapphire band of young, hot stars. But what makes these structures so extraordinary isn't just their beauty, it's the precision of their formation, a testament to gravity's ability to turn chaos into symmetry. The birth of a ring galaxy hinges on a perfect cosmic alignment. The smaller galaxy must plunge almost dead center through the larger one's disk, like an arrow hitting a target. This direct hit sends a shockwave racing outward at hundreds of kilometers per second, sweeping up gas and triggering a firestorm of star formation in its wake. The original galaxy's core remains intact, but its spiral arms are obliterated, replaced by that luminous ring. Unlike the messy, drawn-out mergers of spiral galaxies, ring formations are fleeting masterpieces. Within a few 100 million years, the ring expands and fades, leaving behind an elliptical galaxy with no trace of brilliance. What's astonishing is how these collisions expose the hidden anatomy of galaxies. The pristine rings act like X-rays, revealing the distribution of gas and dark matter in the original disk. In the Cartwheel Galaxy, for instance, the ring's vibrant blue clusters trace the shockwave's path, while infrared telescopes uncover hidden strands of dust woven through the structure. These details help astronomers map how galaxies absorb and redistribute energy during collisions, a process that shapes everything from star formation to black hole growth. Yet ring galaxies are more than just scientific curiosities. They're cosmic time capsules, capturing a single violent moment in a galaxy's life with startling clarity. While most collisions leave behind tangled wrecks of stars, rings offer a snapshot of the instant when chaos and order briefly balanced. And though they're rare, fewer than 1 in 1,000 galaxies sport this structure. Each one is a reminder of the universe's capacity for unexpected artistry. Now, as we turn our gaze from these shimmering rings to the turbulent hearts of colliding galaxies, a new question arises. What happens when the most destructive forces in the cosmos, supermassive black holes, are thrown together by gravity's unrelenting pull? The answer lies in the darkest, most energetic corners of the universe. At the heart of every galactic collision lies a hidden engine of unimaginable power, an active galactic nucleus, or AGN. When galaxies merge, their swirling gas and dust don't just ignite starbursts. Vast rivers of material cascade toward the supermassive black holes at their cores, feeding these cosmic monsters in a spectacular cosmic feast. As matter spirals inward, friction heats it to millions of degrees, creating a swirling disk of superheated plasma that outshines every star in the galaxy combined. This is no ordinary black hole. It's a quasar, the universe's most luminous beacon, capable of shining with the brightness of 1 trillion suns from across the cosmos. What makes quasars so extraordinary isn't just their brilliance, it's their role as cosmic historians. By studying their light, astronomers have uncovered a startling pattern. Quasars were far more common in the early universe, when galactic collisions happened 10 times more frequently. Each quasar is like a fingerprint, its spectrum revealing the composition of gas swallowed during the merger. Some quasars show traces of heavy elements forged in previous generations of stars, evidence that collisions don't just destroy, but recycle the building blocks of planets and life. But AGN aren't just passive observers of galactic mergers, they actively reshape them. The energy pouring from a quasar's jets can blow gas out of its host galaxy at nearly the speed of light, a process called quasar feedback. Imagine a cosmic hurricane, stripping away the raw materials for future stars and effectively putting a brake on galactic growth. This feedback solves a long-standing mystery: why the universe isn't overflowing with giant galaxies. Without quasars regulating star formation during mergers, galaxies would have grown unchecked, devouring all available gas long ago. The legacy of these violent events extends far beyond the galaxies themselves. Quasars and other AGN act as cosmic forges, blasting heavy elements like carbon, oxygen, and iron into intergalactic space. When two galaxies collide, their supermassive black holes don't just feast, they belch, spewing enriched material across millions of light years. These elements, forged in stellar furnaces and scattered by AGN-driven winds, become the seeds for future generations of stars, planets, and even life. The iron in your blood, the calcium in your bones, they were likely forged in the heart of a quasar triggering merger billions of years ago. Now, as we trace these elements back to their origins, we uncover an even deeper connection between galactic collisions and the chemistry of the cosmos. The same violent encounters that birth quasars also scatter their heavy elements across the universe, weaving a tapestry of creation that stretches from the hearts of colliding galaxies to the atoms that make up our world. Every atom in your body, the oxygen in your lungs, the carbon in your cells, even the gold in your jewelry, was forged in the heart of a dying star and scattered across the cosmos by the very collisions we've been exploring. When galaxies collide, they don't just rearrange stars, they unleash a cosmic recycling program on an unimaginable scale. Take something as simple as the iron in your blood. It likely began in a massive star that exploded as a supernova billions of years ago, its shockwaves hurling newly forged elements into space. But without galactic collisions, those precious atoms might have remained trapped in isolated pockets of the universe, never mingling with the gas clouds that would one day form our solar system. The most dramatic element factories emerge during starbursts triggered by mergers. As gas clouds slam together, they birth massive stars that live fast and die young, some lasting just a few million years before exploding as supernovae. These violent deaths seed their surroundings with oxygen, silicon, and sulfur. But for heavier elements like gold, platinum, and uranium, an even more exotic process is needed: neutron star mergers. When two neutron stars, the ultradense remnants of dead stars, collide in the wake of a galactic crash, they create ripples in spacetime and forge enough gold in a single event to outweigh our entire planet. The James Space Telescope recently spotted the aftermath of such a collision, its infrared eyes detecting the telltale glow of freshly minted heavy elements in a distant, merger-ravaged galaxy. This interstellar alchemy doesn't just happen randomly, it follows gravity's roadmap. Galactic collisions create turbulent flows that mix enriched gas with pristine hydrogen, like stirring cream into coffee. The resulting brew becomes the raw material for new stars and planets, each generation richer in heavy elements than the last. Our own solar system is a product of this recycling program. Its planets built from stardust that may have passed through multiple galaxies before finding its way here. Dwarf galaxies, often overlooked in this cosmic drama, play a surprisingly vital role. These small, gas-rich galaxies are like cosmic crucibles, where frequent collisions trigger intense but localized star formation. Without the gravity to hold onto their enriched gas, they lose it to larger neighbors during close encounters, effectively donating their elemental wealth to the galactic community. The Large Cloud, a dwarf galaxy orbiting the Milky Way, is a prime example. Its recent bout of star formation, likely triggered by a near miss with our galaxy, has peppered its structure with supernova remnants whose ejected elements will one day seed future stellar nurseries. This recycling isn't just a historical curiosity, it's ongoing. Right now, supernovae in colliding galaxies like the antennae are forging elements that may someday become part of distant solar systems. The gold in your ring, the uranium powering nuclear reactors, even the calcium in your bones, they're all travelers on a billion-year journey, their paths shaped by the same gravitational dances that twist galaxies into new forms. And as we look deeper into the universe, we find that without these violent, creative encounters, the cosmic palette would be far less vibrant. A universe of hydrogen and helium, devoid of the complexity that makes planets and life possible. Now let's zoom in on these unsung heroes of element production, the dwarf galaxies, where collisions may be smaller in scale, but their contributions to the universe's chemical diversity are anything but insignificant. Dwarf galaxies may lack the grandeur of spirals or the sheer size of ellipticals, but don't let their modest stature fool you. These tiny cosmic workhorses are the unsung heroes of galactic evolution. While titanic mergers like the impending Milky Way Andromeda collision steal the spotlight, it's the quiet, relentless merging of dwarf galaxies that laid the foundation for the universe we see today. Picture a bustling cosmic construction site. Over billions of years, countless dwarf galaxies, some no larger than a globular cluster, clumped together under gravity's pull, their gradual collisions forming the first seeds of larger galaxies. The Milky Way itself likely began as a swarm of these diminutive building blocks, their stars and dark matter slowly coalescing into the grand spiral we call home. Take the large cloud, our galaxy's most prominent dwarf companion. Though it's just 1/10 the mass of the Milky Way, its eventual merger with us will be far gentler than the Andromeda collision, more like a slow-motion embrace than a head-on crash. Already, its gravitational tug warps our galaxy's outer gas clouds, and in about 2.5 billion years, it'll spiral inward, its stars gradually blending with ours. But here's the twist. While the merger itself will be subtle, its aftermath could be transformative. The LMC's rich reservoirs of gas might ignite a new wave of star formation, painting the Milky Way's disk with fresh stellar nurseries. What makes dwarf mergers so special isn't their spectacle, it's their purity. Unlike massive galaxies, which are often bloated with recycled gas and ancient stars, many dwarfs are pristine time capsules, their chemistry preserving clues about the early universe. The ultra-faint dwarf galaxies orbiting the Milky Way, for instance, contain some of the oldest, most metal-poor stars ever found, celestial fossils from an era before heavy elements were widespread. When these dwarfs merge, they deliver these primordial ingredients to larger galaxies, effectively seasoning them with the raw materials of the cosmos, youth. But the real magic happens in galactic clusters, where dwarfs play out their collisions on a crowded stage. In dense environments like the Virgo cluster, dwarf galaxies don't just merge with giants, they frequently collide with one another, creating a hierarchical assembly line of galaxy growth. Some of these encounters produce bizarre hybrids, like the recently discovered fossil dwarfs galaxies so thoroughly mixed that their original components are indistinguishable. Others, like the tantalizingly named blue nuggets, are compact dwarfs caught mid-merger, their cores blazing with star formation as their outer layers are stripped away by tidal forces. Studying these small-scale mergers is like watching the universe build itself in miniature. Computer simulations reveal that without dwarfs, galaxies like ours would lack their vast halos of dark matter and ancient stars. Their collisions, though gentle compared to the cosmic car crashes of larger galaxies, are the quiet architects of structure, weaving the invisible framework that holds the cosmos together. And as we peer deeper into the universe's past, we're finding that the earliest galaxies, tiny, turbulent, and dwarf-like, relied on these same mergers to the growth of everything that followed. Now, as we shift our gaze from these miniature builders to the crowded metropolises of galactic clusters, we'll see how collisions operate on an even grander scale, where hundreds of galaxies, bound by gravity's unrelenting grip, engage in a ceaseless dance of destruction and renewal. The lessons learned from dwarfs are just the beginning. Galaxy clusters are the ultimate proving grounds for cosmic collisions, where gravity orchestrates mergers so immense they defy comprehension. Imagine hundreds, Even thousands of galaxies bound together in a single, sprawling metropolis, each member moving at thousands of kilometers per second through a superheated soup of gas. When these clusters collide, the energy released rivals the combined light of every star within them. The Bullet Cluster stands as one of the most dramatic examples. Here, two galaxy clusters plowed through each other at staggering speeds, but something strange happened. Their dark matter kept right on moving, unaffected, while their gas clouds, hot, glowing, and packed with normal matter, slammed together like celestial traffic jam, heating to over 100 million degrees. This cosmic fender bender gave astronomers their first clear proof that dark matter exists, and that it interacts with the universe in ways entirely unlike ordinary matter. What makes these collisions so revealing isn't just their scale. It's how they expose the invisible forces shaping the cosmos. As galaxies within clusters merge, their supermassive black holes often spiral toward one another, unleashing gravitational waves that ripple through space-time. The gas between galaxies, meanwhile, doesn't just sit idle. It's compressed, shocked, and twisted into intricate shapes, emitting X-rays so intense they can be seen across billions of light years. These collisions are also cosmic particle accelerators, generating magnetic fields strong enough to bend the paths of high-energy electrons, which then emit synchrotron radiation, a ghostly glow that traces the otherwise invisible magnetic web connecting galaxies. But the real surprise lies in how these events sculpt galactic magnetism itself. When clusters collide, their magnetic fields don't simply cancel out or fade away. They stretch, tangle, and amplify, like threads woven into a knot. Simulations show these fields can grow exponentially during a merger, channeling turbulent energy across vast distances. In the Coma cluster, for instance, astronomers have detected magnetic filaments stretching over 500,000 light-years, structures likely forged in ancient collisions and now acting as cosmic conductors for high-energy particles. These magnetic fingerprints aren't just curiosities, they're clues to some of the universe's deepest mysteries. The same forces that twist magnetic fields during collisions also accelerate particles to nearly the speed of light, creating ultra-high-energy cosmic rays, some of the most energetic phenomena known. And because magnetic fields influence how gas cools and collapses, they ultimately determine where and when new stars can form in the aftermath of a merger. Without them, the universe might lack the delicate balance needed to birth galaxies at all. Yet for all their power, cluster collisions unfold with eerie silence. No sound carries through the vacuum of space, no shockwave reaches our telescopes, just the faint whisper of radio waves and X-rays, hinting at the violence below the surface. It's a reminder that even the grandest structures in the cosmos are governed by forces we're only beginning to understand, their secrets written in the language of magnetism, gravity, and light. And as we peer deeper into these cosmic laboratories, we're not just watching galaxies collide, we're witnessing the universe itself refine the very laws that shape its evolution. Magnetic fields in galaxies might be invisible to our eyes, but their influence is anything but subtle, especially when galaxies collide. Picture an immense, tangled web woven through every spiral arm and gas cloud, directing the flow of cosmic material like an unseen conductor. During a collision, these magnetic fields don't just passively watch the chaos unfold. They're stretched, twisted, and supercharged, becoming powerful sculptors in their own right. Take the famous antennae galaxies, where observations of polarized light reveal magnetic fields amplified to strengths thousands of times greater than Earth's, their lines contorted into chaotic loops by the gravitational turmoil. What's astonishing is how these fields shape the aftermath of a collision. As gas clouds slam together, magnetic pressure can channel their motion, preventing some regions from collapsing into stars while compressing others into dense, glowing nurseries. In the Tadpole Galaxy's colossal tidal tail, a stream of stars flung across space by a past encounter, magnetic fields act like cosmic rails, guiding charged particles and cosmic rays along their length. Without these fields, the tail's delicate structure might dissolve into chaos, its gas diffusing into the void. Instead, we see luminous filaments, their glow partly fueled by electrons spiraling along magnetic field lines at nearly the speed of light. Polarized light holds the key to mapping this hidden architecture. When light scatters off dust grains aligned by magnetic fields, it becomes polarized, vibrating in a preferred direction. Telescopes like ALMA and the VLA capture this subtle signal, revealing how fields in merging galaxies reorganize themselves, sometimes forming colossal magnetic bridges between colliding partners. These bridges aren't just curiosities, they're cosmic highways funneling gas and energy between galaxies long after their initial encounter. The implications stretch far beyond aesthetics. Magnetic fields regulate how quickly gas cools, determining whether a galaxy births new stars or stagnates. In some mergers, amplified fields act like brakes, slowing gas collapse and quenching star formation. In others, they focus turbulence into precise zones, igniting starbursts so intense they outshine entire galaxies. Understanding this duality, how magnetic fields can both nurture and stifle creation, helps explain why colliding galaxies evolve so differently, even under similar conditions. Now, as we peer deeper into the universe's quieter corners, we find collisions leaving behind an entirely different legacy. Not brilliant starbursts or magnetic maelstroms, but ghostly, faint galaxies that defy expectations. These ultra-diffuse galaxies, floating like cosmic jellyfish in the void, may hold clues to how the gentlest mergers shape the cosmos. Their story begins not with a bang, but with a whisper. Ultra-diffuse galaxies drift through the cosmos like celestial ghosts. Vast, faint, and almost transparent, their stars spread so thin they barely register against the darkness. These enigmatic structures defy expectations, stretching as wide as the Milky Way but containing just 1% of its stars. Some appear almost empty, their sparse stellar populations floating in immense halos of dark matter. How do such fragile galaxies survive in a universe dominated by gravity's relentless pull? The answer may lie in the aftermath of violent collisions, where the chaos of a merger scatters stars into orbits so wide they become nearly invisible. Take Dragonfly 44, a galaxy in the Coma cluster that stunned astronomers when they realized its dark matter halo rivaled the Milky Way's. Yet its stars were so few you could practically count them. One theory suggests it's the remnant of a high-speed collision, where two galaxies clipped each other just enough to strip away their gas and disrupt star formation, leaving behind a skeletal structure of old stars and dark matter. Others, like NGC 1052DF2, challenge even this explanation, with almost no dark matter at all. These outliers hint at an even stranger origin. Perhaps they're failed galaxies, born from gas clouds too turbulent to coalesce into denser structures, their stars sputtering into existence like a candle flickering in the wind. What makes ultra-diffuse galaxies so fascinating isn't just their unusual forms, it's what they reveal about the hidden diversity of galactic evolution. In crowded galaxy clusters, collisions are frequent and brutal, leaving behind these faint survivors as cosmic. Yet some ultra-diffuse galaxies flourish in isolation, far from the gravitational turmoil of clusters, suggesting alternative paths to their formation. Their very existence forces astronomers to rethink long-held assumptions. If galaxies can be this faint, this spread out, how many have we missed? Surveys now suggest they might be astonishingly common, lurking undetected in our cosmic backyard, their dim light drowned out by brighter neighbors. Studying these ghosts offers more than just academic curiosity. Their fragile structures act as cosmic stress tests, revealing how galaxies respond to extreme environments. Some, like the ultra-diffuse galaxies in the Virgo cluster, sport bizarre, elongated shapes, telltale signs of tidal forces stretching them like taffy during close encounters. Others show evidence of ancient star formation abruptly cut short, as if their gas was ripped away in a long-ago collision. By piecing together their histories, we're uncovering a hidden chapter of galactic evolution, one where violence and quiet dissolution shape the cosmos as much as grand spirals and brilliant starbursts. Now, as we shift our gaze from these ethereal remnants to the dynamic hearts of galaxies, a new question emerges. How do collisions alter the very spin of galaxies, twisting their orderly rotations into chaos? The answer lies in the interplay of momentum, gravity, and the invisible hand of dark matter, a dance that begins with a single, fateful encounter. Galaxies spin like cosmic tops, their vast disks of stars and gas rotating in a delicate balance held together by gravity. But when two galaxies collide, that orderly motion is thrown into chaos, like two whirlpools merging in a stormy sea. The resulting gravitational tug-of-war can do more than just distort shapes. It can completely rewrite a galaxy's rotation, flipping its spin axis sideways, slowing it to a crawl, or even reversing its direction entirely. Take NGC 4569, a galaxy caught mid-merger with a smaller companion. Observations reveal its spiral arms twisting in opposite directions, a clear sign of competing angular momentum as the two galaxies wrestle for dominance. The key to understanding these transformations lies in angular momentum, the same physics that keeps a figure skater spinning faster as they pull their arms in. During a collision, the combined angular momentum of the merging galaxies doesn't just vanish. It's redistributed, often in unpredictable ways. Imagine two spinning tops colliding on a table. Depending on their angles and speeds, they might spiral apart, lock into a new shared rotation, or even topple over entirely. Galaxies behave similarly with one critical difference. Their collisions unfold over hundreds of millions of years, giving gravity ample time to sculpt the final product. Some mergers produce galaxies with exaggerated spins, their stars whirling at breakneck speeds. Others, like many massive ellipticals, barely rotate at all, their stars moving in random orbits after their angular momentum was canceled out during the collision. This dance of spin and momentum leaves behind cosmic fossils, galaxies whose rotations encode the history of past collisions. The giant elliptical galaxy Messier 87, for example, shows almost no net rotation, a telltale sign of a violent merger that scrambled its original spin. In contrast, the fast-rotating spiral galaxy NGC 2778 owes its rapid twirl to a gentler encounter, one that injected fresh angular momentum without fully disrupting its disk. By studying these variations, astronomers can reconstruct a galaxy's merger history, much like a paleontologist pieces together an ancient creature's life from its bones. But mergers don't just alter rotation. They can also erase it entirely, leaving behind galaxies that defy classification. Some of the universe's most peculiar structures, like polar ring galaxies, are the aftermath of these gravitational upheavals. These rare objects feature a central galaxy surrounded by a ring of stars, gas, and dust orbiting perpendicular to the main disk, a clear relic of a past collision where the victim galaxy's angular momentum was flipped 90 degrees. The Cartwheel Galaxy, with its off-center ring and distorted spokes, is another stellar example. Its bizarre shape the result of a smaller galaxy punching through its disk like a bullet through a bicycle wheel. What makes these transformations so crucial is their role in galactic evolution. Rotation isn't just about motion, it's about stability. A galaxy's spin helps regulate star formation, shapes its magnetic fields, and even influences the growth of its central black hole. When collisions alter that spin, they don't just change how a galaxy looks, they change how it lives, ages, and interacts with its surroundings. And as we peer deeper into the cosmos, we're finding that these rotational fingerprints are everywhere, from the stately spirals of the local universe to the chaotic mergers of the distant past. Now, as we turn our attention to the fossils of these collisions, galaxies frozen in time, their structures preserving the echoes of ancient encounters, we'll uncover how the universe's most violent events can leave behind some of its most enduring relics. NGC 1132 drifts through space like a cosmic relic, its smooth, golden glow betraying no trace of the violent past that shaped it. This fossil galaxy, as astronomers call it, is the end product of a collision so ancient its scars have long since faded, a celestial tombstone marking where multiple galaxies once merged into one. Unlike younger ellipticals still speckled with blue star-forming regions, NGC 1132 stars are uniformly old and red, their formation cut off billions of years ago when its last gas reserves were stripped away or devoured by its central black hole. What makes these fossil galaxies so revealing isn't just their quiet present, but the stories etched into their very structure. Their perfectly smooth profiles and enormous dark matter halos suggest they formed through dry mergers collisions between gas-poor galaxies too depleted to ignite new, leaving behind only the blended remains of their stellar populations. The intergalactic medium surrounding these fossils tells an equally dramatic tale. When galaxies collide, they don't just reshape themselves. They send shockwaves rippling through the sparse gas between galaxies, heating it to millions of degrees and enriching it with heavy elements forged in supernovae. The Perseus cluster offers a stunning example. X-ray telescopes reveal vast cavities and sound waves in its superheated gas, carved out by jets from a supermassive black hole likely stirred to activity during a past merger. These disturbances aren't just cosmic curiosities, they regulate the entire cluster's evolution. By preventing gas from cooling and collapsing into new galaxies, merger-driven feedback ensures some regions remain frozen in time, their gas too turbulent to form stars. Yet collisions don't always sterilize their surroundings. In the Leo Ring, a massive loop of hydrogen gas orbiting two ancient galaxies, we see the opposite phenomenon, a merger's debris becoming the raw material for future cosmic generations. This 300,000 light-year-wide structure, likely forged during a long-ago collision, remains rich in pristine gas untouched by star formation. Given enough time, gravity may yet weave this relic into new galaxies, proving that even the aftermath of violence can seed creation. The intergalactic medium isn't just a passive backdrop. It's an active participant in the collision cycle, absorbing energy, transporting elements, and setting the stage for the next act in the universe's endless drama of destruction and renewal. When galaxies collide, they don't just reshape themselves. They send shockwaves of enriched gas surging into the vast, near-empty expanses between galaxies. This intergalactic medium, often imagined as a barren void, is anything but empty. It's a dynamic reservoir, a cosmic recycling center where the fallout from collisions becomes the raw material for new creation. Picture a galactic fountain. As two galaxies merge, their gravitational turmoil ejects torrents of gas, laced with heavy elements forged in stellar furnaces, into the surrounding space. This gas, heated to millions of degrees, glows faintly in X-rays, tracing delicate filaments that stretch across millions of light years. Over time, gravity coaxes these ejected clouds to cool and condense, pulling them back into galaxies or depositing them into the halos of dark matter that anchor cosmic structures. The process isn't just poetic, it's fundamental to how galaxies evolve. Take the Perseus cluster, where X-ray observations reveal vast, rippling waves in the intergalactic gas, like fingerprints left by ancient mergers. These disturbances aren't mere echoes, they're active participants in galactic ecology. As ejected gas cools, it trickles back into galaxies in a slow-motion rainfall, replenishing the fuel for future star formation. In some cases, this recycled material becomes the backbone of entire new galactic arms, as seen in the so-called cold streams feeding distant spiral galaxies. Without this cycle, galaxies would exhaust their gas supplies within a few billion years, leaving the universe dark and lifeless. But the intergalactic medium isn't just a passive recipient of galactic debris, it's a sculptor in its own right. The heavy elements ejected during collisions, carbon, oxygen, iron, transform this primordial soup from a featureless sea of hydrogen and helium into a chemically enriched brew. These elements, forged in the hearts of stars and scattered by supernovae, become the building blocks for rocky planets, organic molecules, and even life itself. The oxygen we breathe, the calcium in our bones, likely spent eons drifting in the intergalactic medium before being swept up by a galaxy like our own. What's astonishing is how finely tuned this cycle is. Too much ejection and galaxies starve, too little and the universe remains chemically sterile. Collisions strike the balance, acting as cosmic regulators that distribute matter across scales. Simulations show that without these violent encounters, the intergalactic medium would lack the heavy elements needed to cool efficiently, stifling the birth of new galaxies. It's a delicate feedback loop. Collisions enrich the medium fuels future galaxies, and those galaxies eventually collide again, perpetuating the cycle. This interplay between galaxies and their surroundings holds keys to some of cosmology's biggest questions. By studying the fingerprints of collisions in the intergalactic medium, its temperature fluctuations, chemical gradients, and magnetic fields, we can reconstruct the merger histories of entire galaxy clusters. These clues reveal how the universe transitioned from a smooth, featureless early state to the intricate web of structures we see today. The intergalactic medium is more than a bystander. It's the connective tissue of the cosmos, a living record of gravity's endless work. And now, as we turn our gaze to the most luminous objects in the universe, we'll see how collisions don't just shape galaxies and their surroundings. They awaken the sleeping giants at their cores. When supermassive black holes are stirred by mergers, they can transform into quasars, beacons of light so brilliant they outshine entire galaxies. But their story begins with the same gravitational dances we've witnessed on every scale, from the faintest dwarf galaxies to the richest clusters. The stage is set for the universe's most dazzling performance. Quasars are the universe's ultimate powerhouses, blazing beacons so luminous they can outshine entire galaxies from billions of light years away. But what fuels these cosmic lighthouses? The answer lies in the chaos of galactic collisions. When two galaxies merge, their gravitational dance doesn't just rearrange stars. It funnels vast rivers of gas and dust toward the supermassive black holes lurking at their cores. As this material spirals inward, friction heats it to millions of degrees, creating an accretion disk so bright it can eclipse every star in its host galaxy combined. The result is a quasar, a phenomenon so energetic it defies comprehension. The most astonishing quasars aren't just bright, they're time machines. Because light takes time to travel, the quasars we observe in the distant universe are snapshots of a younger, more violent cosmos. Back then, galaxies were packed closer together, colliding 10 times more often than they do today. Each merger was a potential quasar trigger, with fresh gas flooding into central black holes and igniting outbursts of radiation that could last millions of years. The quasar SDSS J0100 plus 2802, for instance, shines with the brightness of 400 trillion suns, a relic of an era when galactic collisions were the universe's primary construction method. But quasars aren't just relics, they're active participants in shaping their galaxies. The energy pouring from a quasar's jets can blast gas out of its host galaxy at nearly the speed of light, a process known as quasar feedback. Imagine a cosmic hurricane, stripping away the raw materials for future stars and effectively putting a brake on galactic growth. This feedback solves a long-standing mystery: why the universe isn't overflowing with giant galaxies. Without quasars regulating star formation during mergers, galaxies would have devoured all available gas eons ago, leaving the cosmos dark and stagnant. What's truly remarkable is how these collisions leave their mark on quasars themselves. The light from a quasar carries chemical fingerprints, traces of heavy elements like carbon, oxygen, and iron forged in earlier generations of stars. These elements, ejected during past collisions and recycled into the quasar's accretion disk, reveal a history of cosmic violence written in spectral lines. By analyzing these signatures, astronomers can reconstruct the merger history of the quasar's host galaxy, uncovering how many collisions it survived and how much gas it consumed along the way. Yet quasars are more than just cosmic record keepers. They're also engines of creation. The same jets that blast gas outward also inject energy into the intergalactic medium, heating it and enriching it with heavy elements. Over time, this enriched material cools and falls back into galaxies, seeding future generations of stars and planets. The iron in your blood, the calcium in your bones, they may have once cycled through the heart of a quasar, forged in the fires of a long-ago collision. Now, as we turn our gaze from these brilliant beacons to their lingering aftermath, a new chapter unfolds. The winds unleashed by quasars and galactic collisions don't just fade into the void, they sculpt the cosmos on scales beyond imagination, carrying the echoes of violence into the farthest reaches of space. When galaxies collide, they don't just rearrange stars, they unleash cosmic hurricanes. These aren't ordinary winds, but supersonic tempests roaring outward at thousands of kilometers per second, carrying enough energy to reshape entire galaxies. Picture the Starburst Galaxy M82, where collision-triggered star formation has ignited a maelstrom so powerful it's visible across the electromagnetic spectrum. X-ray telescopes reveal filaments of million-degree gas stretching 40,000 light-years into space, while infrared images show cooler material blown outward like cosmic confetti. These galactic winds aren't mere byproducts of mergers. They're universe-shaping forces, capable of ejecting more mass than all the stars in our Milky Way combined. What makes these outflows so transformative is their dual nature. On one hand, they're destructive, stripping galaxies of the gas needed to form new stars. Observations of the Mice galaxies show winds so intense they've emptied entire regions of star-forming material, leaving behind galactic deserts. Yet paradoxically, these same winds are creative. As they blast through intergalactic space, they carry heavy elements forged in stellar furnaces: oxygen, carbon, iron, seeding future generations of stars and planets far from their birthplace. The iconic cartwheel galaxies spoke like filaments, glowing with ejected metals, demonstrate this process in action. A collision's destruction scattering the building blocks of life across the cosmos. The physics behind these winds is as fascinating as their effects. Starbursts triggered by mergers produce thousands of supernovae in quick succession, their combined shockwaves punching holes in galactic gas disks. Radiation from newborn massive stars then heats this punctured material, creating expanding bubbles that merge into galaxy-scale outflows. In some extreme cases, like the nearby galaxy NGC 1291, winds become so powerful they escape their host entirely, forming vast metal-rich halos detectable millions of light-years away. These halos act as cosmic reservoirs, storing enriched gas until gravity someday pulls it back, a galactic water cycle playing out over billions of years. Now shift your gaze to an entirely different merger remnant: polar ring galaxies, the universe's celestial carousels. These rare objects, only about one in every 1,000 galaxies, feature a central bulge surrounded by a ring of stars, gas, and dust orbiting at a 90-degree angle to the main disk. The most striking examples, like NGC 4650A, look like glowing cosmic bullseyes, their perfect perpendicular rings defying conventional galactic structure. These bizarre formations are the aftermath of a precise cosmic collision, where a smaller galaxy plunges edge-on through a larger disk, its stars torn apart by tidal forces and recast into a swirling ring. The creation of a polar ring is gravity's delicate ballet. As the intruder galaxy passes through, its material doesn't just scatter randomly. It settles into stable orbits perpendicular to the victim galaxy's rotation, preserved by the same conservation of angular momentum that keeps a spinning top upright. Over time, this ring becomes a snapshot of the collision's geometry, its orientation revealing the exact angle of impact. Some polar rings, like that of AM0644741, even show evidence of ongoing star formation, proving these structures aren't mere relics but active galactic components. What makes polar rings so valuable to astronomers isn't just their beauty, it's what they reveal about dark matter. By measuring how stars move within these perpendicular rings, scientists can map the host galaxy's gravitational field in 3 dimensions, uncovering the otherwise invisible dark matter halo's true shape. The results are surprising. Many polar ring galaxies have flattened dark matter distributions, challenging assumptions about how these mysterious halos form during mergers. Like cosmic forensic evidence, each ring preserves clues about its violent birth and the unseen forces that shaped it. From the tempestuous winds of starburst galaxies to the serene rings of these celestial oddities, galactic collisions prove that destruction and creation are inseparable cosmic partners. Whether ejecting life-giving elements across intergalactic space or sculpting structures of improbable symmetry, these violent encounters don't just change galaxies. They redefine our understanding of how the universe builds, destroys, and rebuilds itself on the grandest scales. Polar ring galaxies stand as some of the universe's most mesmerizing anomalies, celestial carousels where rings of stars, gas, and dust spin at right angles to their host galaxies, defying conventional structure. Take NGC 4650A, a stunning example whose luminous ring orbits perpendicular to its central disk like a cosmic hula hoop frozen mid-spin. These rare formations aren't random accidents. They're the delicate handiwork of precise galactic collisions. Imagine a smaller galaxy plunging edge-on through a larger disk, its stars shredded by tidal forces and reassembled into a swirling ring by gravity's patient choreography. The result is a galactic hybrid so improbable that only 1 in 1,000 galaxies exhibits this peculiar architecture. What makes polar rings so invaluable to astronomers isn't just their striking appearance. It's the secrets they hold about angular momentum, the invisible force governing cosmic rotation. During a merger, the intruder galaxy's material doesn't scatter chaotically. Instead, it settles into orbits perpendicular to the victim galaxy's spin, preserved by the same physics that keeps a spinning top upright. The ring becomes a cosmic gyroscope, its orientation locked to the collision's exact geometry. Some, like the polar ring surrounding UGC 9792, even showcase ongoing star formation within the ring itself, proving these structures aren't static relics but dynamic, evolving systems. Beyond their beauty, these oddities serve as natural laboratories for studying dark matter. By tracking how stars move within the perpendicular rings, scientists can map the host galaxy's gravitational field in 3 dimensions, revealing the shape of its otherwise invisible dark matter halo. Surprisingly, many polar ring galaxies feature flattened dark matter distributions, challenging long-held assumptions about how these halos form. The ring's stability over billions of years, despite the host galaxy's relentless rotation, suggests dark matter acts as an unseen scaffold, anchoring the structure against centrifugal forces that should tear it apart. The rarity of polar rings hints at the fine balance required for their creation. Too forceful a collision, and the intruder galaxy disintegrates completely, too gentle and no ring forms. Only when the merger's angle, speed, and mass ratio align just right does gravity sculpt this celestial masterpiece. Even then, the rings is finite. Over eons, gravitational interactions with the host galaxy will warp and disperse it, leaving behind only subtle kinematic fingerprints, telltale stellar motions betraying the violence of its birth. These galactic oddities remind us that collisions don't just destroy or merge, they can engineer structures of breathtaking precision. As we shift our focus from individual marvels to broader patterns, a new question emerges. How do these collisions collectively shape the demographics of galaxies across the cosmos? From the smallest dwarfs to the mightiest clusters, each encounter leaves an imprint on the universe's grand census of galactic forms. The cosmos is a grand museum of galactic diversity, and every galaxy's shape tells a story of its past encounters. Wander through a quiet cosmic neighborhood like our local group, and you'll find spirals like the Milky Way and Andromeda, their elegant arms swirling undisturbed. But venture into the heart of a dense cluster like Coma or Virgo, and the scene shifts dramatically. Elliptical galaxies dominate here, their smooth, football-like shapes devoid of spiral structure. This isn't random. It's the direct result of collisions, with each galaxy's form acting as a fossil record of its gravitational history. Spirals thrive where interactions are rare, their delicate disks preserved over billions of years. Ellipticals, by contrast, are the battle-scarred veterans of cosmic mergers, their stars jostled into chaotic orbits by repeated encounters. What's fascinating is how this distribution mirrors the universe's evolving dynamics. In the early cosmos, spirals were far more common, their gas-rich disks furiously forming stars. But as galaxies congregated into clusters, drawn together by dark matter's invisible web, collisions became inevitable. Each merger stripped away gas, randomized stellar orbits, and eventually erased spiral features, leaving behind the featureless ellipticals we see today. The giant elliptical Messier 87, anchored at Virgo's center, didn't start as a behemoth. It grew by devouring smaller neighbors, its smooth profile the final signature of countless digested galaxies. This pattern isn't just about morphology, it's a window into cosmic environments. Find a galaxy with delicate spiral arms and you're likely looking at a cosmic hermit, one that's avoided major mergers. Spot an elliptical surrounded by a swarm of smaller galaxies, and you're witnessing a predator in its prime, its gravity still pulling in fresh prey. Even the rare lenticular galaxies, hybrids with disks but no spiral arms, hint at a middle ground, perhaps the result of a near-miss collision that stirred a spiral's gas without fully destroying it. The future of collision research lies in connecting these galactic demographics to the universe's larger narrative. Upcoming telescopes like the observatory will map billions of galaxies, tracing how their shapes correlate with environment and age. Meanwhile, supercomputer simulations grow ever more sophisticated, reconstructing the precise mergers that could turn a spiral into an elliptical over eons. Together, these tools will let us rewind cosmic history, revealing not just how individual galaxies collided, but how those encounters collectively shaped the universe's vast, evolving tapestry of forms. And as we peer forward, new mysteries emerge. Could some galaxies defy these trends, surviving against the odds? What role do smaller mergers play in shaping a galaxy's destiny? The answers lie in the faintest galactic outliers, the relics and rebels that challenge our understanding of cosmic evolution. Their stories are still being written, one collision at a time. The next decade promises a revolution in our understanding of galactic collisions, as a new generation of telescopes and instruments turns its gaze toward the cosmic dance of gravity. The observatory, set to begin its legacy survey of space and time in 2025, will scan the entire southern sky every few nights, detecting millions of interacting galaxies, many so distant their light has traveled for billions of years to reach us. Unlike previous surveys that captured static snapshots, this relentless monitoring will create a cosmic time-lapse, revealing how mergers unfold across different epochs. Imagine watching the slow-motion collision of two spirals not just as a single frame, but as a flickering sequence where tidal tails grow, starbursts ignite, and gas clouds collapse, all in unprecedented detail. This isn't just about more data, it's about witnessing the dynamic processes that shape galaxies in real time. Equally transformative are the gravitational wave observatories preparing to tune into the universe's most violent mergers. While LIGO and Virgo currently detect collisions of stellar mass black holes, future space-based detectors like LISA will track the slow spiral of supermassive black holes, the behemoths lurking at galactic centers. These events emit gravitational waves with wavelengths so vast they take years to oscillate, carrying whispers from an era when the first galaxies were assembling. By decoding these signals, scientists hope to solve enduring mysteries. Do supermassive black holes always merge, or can they stall just shy of collision? What role did early mergers play in seeding the cosmic web? The answers could rewrite our theories of galaxy formation. But the breakthroughs won't stop there. The James Space Telescope's infrared vision is already peering through dust clouds to study the chemistry of colliding galaxies, revealing how they enrich the universe with heavy elements. Meanwhile, the Square Kilometer Array radio telescope will map the invisible hydrogen gas swirling between merging galaxies, tracing the raw material for future stars. Together, these tools form a cosmic detective kit, each instrument uncovering clues the others can't see. What makes this era so thrilling isn't just the technology, it's the potential for surprise. Every time humanity has built a better window into the cosmos, we've stumbled upon phenomena nobody predicted. Perhaps we'll discover mergers that defy current models, or black holes merging in ways that challenge theories. Maybe we'll catch a galaxy in the act of being torn apart by dark matter we still don't understand. One thing is certain. As we stand on the brink of these discoveries, we're not just observers of galactic collisions. We're witnesses to a new chapter in our understanding of the universe's grand narrative. These advances invite us to reflect on a deeper truth. Galactic collisions aren't just events happening out there in the void. They're the architects of complexity, the crucibles where the elements of life are forged and scattered across the cosmos. Every time we gaze at the night sky, we're seeing the aftermath of these ancient encounters, a tapestry woven by gravity's patient hand. And as new telescopes reveal the choreography of merging galaxies in ever greater detail, we're reminded that we too are part of this story, our very existence tied to the celestial dances of the distant past. Galactic collisions do more than reshape the cosmos, they reshape how we see our place within it. Every time two galaxies merge, they shatter the illusion of celestial permanence, revealing a universe in constant flux. Consider this, the tranquil spiral we call home, the Milky Way, will one day vanish, its stars blended into a new galactic entity. This isn't destruction, it's transformation on a scale so vast it redefines our understanding of time itself. These events whisper a humbling truth. The stability we take for granted is fleeting, a momentary pause in gravity's endless dance. Yet there's profound beauty in this impermanence. Collisions forge connections across the cosmos, weaving galaxies into a web of shared history. The iron in your blood, the silicon in Earth's rocks, they were likely forged in the heart of a starburst triggered by an ancient merger, then scattered across space by galactic winds. We're not just observers of this drama, we're products of it, our very atoms carrying echoes of cosmic encounters billions of years old. This interconnectedness transcends distance and time, linking the fate of distant galaxies to the chemistry of life on our planet. What makes these events so captivating isn't just their scale, it's how they expose the limits of human intuition. A galaxy's dwarf civilizations, their collisions unfold slower than continental drift. To witness such processes, even through the fleeting snapshots of telescopes, is to stretch our minds across dimensions we can scarcely grasp. And here lies the paradox. The more we learn about these collisions, the more they reveal how much lies beyond our current understanding. Dark matter's invisible scaffolding, the mysterious recoil of merging black holes, the way galaxies remember their collision histories in their spins, each discovery peels back a layer, only to reveal deeper mysteries waiting beneath. This endless curiosity is perhaps the most human response to galactic collisions. They ignite questions that have driven explorers and thinkers for: where did we come from? What forces shape existence? How do we fit into the grand scheme? Modern astronomy offers answers undreamt of by ancient stargazers, yet the essence remains the same: awe at the universe's grandeur. When the Space Telescope captures two galaxies entwined like dancers, or JWST reveals the infrared glow of their colliding gas clouds, we're not just collecting data. We're continuing a tradition as old as humanity itself, mapping the unknown to find meaning in the vastness. As our journey through the drama of galactic collisions comes to a close, one realization lingers. These events aren't just happening out there in the void. They're part of a story that includes us. The same forces that twist galaxies into new forms also set the stage for planets, life, and the rare privilege of consciousness that lets us bear witness. In the grand tapestry of the cosmos, where even the mightiest structures are transient, our ability to marvel at them may be the most remarkable thread of all. The universe doesn't just collide and create, it wonders, explores, and understands. And that changes everything. Galactic collisions are the universe's most breathtaking symphonies, where gravity acts as both composer and conductor, weaving chaos into creation. These monumental encounters, whether the slow-motion tango of the Milky Way and Andromeda or the violent embrace of the antennae galaxies, don't just reshape individual galaxies, they rewrite the cosmic rulebook. Picture a starburst ignited by colliding gas clouds, its brilliance outshining entire galaxies, or two supermassive black holes spiraling toward a collision so powerful it ripples the fabric of spacetime itself. These aren't just isolated events. They're the engines driving galactic evolution, recycling matter, forging new stars, and seeding the universe with the heavy elements that make planets and life possible. What makes these collisions so extraordinary is their duality. They destroy and create in equal measure, unraveling the orderly spiral arms of galaxies while igniting firestorms of star birth. Take the Tadpole Galaxy, its tail strewn with stellar nurseries, a testament to how gravitational turmoil can birth new worlds even as it tears old ones apart. Or consider the fate of supermassive black holes, which grow by devouring gas stirred up during mergers, only to eventually merge themselves in explosions of energy that can outshine the universe for a fleeting moment. This interplay of destruction and renewal isn't accidental. It's the universe's way of reinventing itself, ensuring that no galaxy, no matter how majestic, remains static forever. Yet for all their violence, galactic collisions also reveal the universe's hidden order. The tidal tails stretching across millions of light years, the delicate rings of polar galaxies, even the faint shells of ancient mergers, all are cosmic fingerprints, clues to gravity's patient craftsmanship. With tools like the James Space Telescope and gravitational wave detectors, we're now decoding these clues like never before, piecing together how collisions built the galaxies we see today. Each discovery peels back another layer, showing us how the faintest dwarf galaxies and the mightiest clusters share a common origin story, written in the language of gravitational encounters. As we stand on the brink of new revelations, from the Milky Way's eventual merger with Andromeda to the detection of ever more distant collisions, we're reminded that these events aren't just cosmic curiosities. They're the heartbeat of the universe, the pulse that drives its endless transformation. And in tracing their echoes across space and time, we're not just uncovering the past, we're glimpsing the future of galaxies yet to be born. So the next time you look up at the night sky, remember, the serene glow of stars hides a dynamic, ever-changing cosmos where even the grandest structures are dancers in gravity's eternal ballet. What fascinates you most about galactic collisions? Is it their destructive power, their creative potential, or the secrets they hold about the universe's origins? Let's keep the conversation going in the comments, and if you've enjoyed this journey through the cosmos, be sure to subscribe for more deep dives into the wonders of space. Until next time, keep